Okay, so once again, we're looking at implicit equations, and we're trying to find equations for tangent lines. So to find a tangent line, we know that to find a tangent line, we know that we need to find the slope, and to find the slope, we know that we need to find the derivative. So I've got this function, and it's going to be a little bit tricky for us to take the derivative of the left-hand side. So I'm gonna pull that over here and think about e to the y as the composition of f of x being e to the x and g of x being y. So my function is f of g of y, sorry, f of g of x. And we know that f prime of e to the x is just e to the x, and the derivative of y, well, g prime would be dy dx. So when I use the chain rule, the derivative of this will be f prime of g of x times g prime of x, which equals e to the y times dy dx. So that's the derivative of this. So we need to take, I jumped ahead a little bit, we need to take the derivative of both sides. The derivative of e to the y um, and the derivative of ln x. We know, because I already found this over on the left, that that equals e to the y times dy dx. And the derivative of ln x, we know that that's 1 over x. So dy dx equals 1 over x times 1 over e to the y. And we're evaluating this at the following points. So we're evaluating that when x equals e, so 1 over e, and when y is 0, so times 1 over e to the 0, and this just equals 1 over e. That's our slope, and that's our slope, and we want to find the tangent line, so y equals our slope times x minus e plus our y value, 0. So these points come from here. This comes from here. So we could simplify that, and we get y equals 1 over e times x minus 1. Now, does that make sense? Well, I think it does if we go and look at our tangent line. We're talking about this point right here. And if we draw the tangent line, it does, in fact, have a y-intercept of -1. So I think we did a good job. Next problem here, we've got this curve defined by the following equation. Now I've given us a graph of this using my implicit grapher, and that's going to help us answer these questions. It says write an equation for the line tangent to the curve at the point 2 comma -1. So we're talking about, let's see, we're talking about this tangent line right there. So we know it's going to have a positive slope. It should have a y-intercept around -2, just graphically. So to find the equation for that tangent line, we have to take implicit differentiation. So let's take the derivative of the left-hand side. So the derivative, and we're going to need to use the product rule in there. And the derivative of 0, well, we know that's going to be 0. So the derivative of y cubed is going to be 3y squared times dy dx plus, now let's take the derivative of that first. So 6x times y plus, and now let's take the derivative of that one. So 3x squared times the derivative of y is just y prime, and the derivative of 13, 0 equals 0. Simplifying this, we get 3y squared times y prime plus 3x squared times y prime equals -6xy. We can factor out a y prime. And then we can solve for y prime. And when we do that, we get that y prime equals -6xy over 3y squared plus 3x squared. And we want to find the derivative when x equals 2 and y equals -1. So at that specific point, um, we will put in 2 and 1 for x and y respectively. We get -6 times 2 times -1 all over 3 times -1 squared plus 3 times 2 squared. Simplifying this, we get 12 over 15, which is 4 over 5. And to find the equation for a line, now that's our slope, and we're looking at this point. The equation for a line is y equals 4/5 x minus 2 uh, minus 1. And if we were to further simplify this, we get 4/5 x minus 8/5 minus 1. So, well, this distributing it minus 8/5 minus 1, and then we could add fractions, but this one is good enough. So there's our equation for our tangent line. And to do that, again, we just did implicit differentiation to find the derivative, and then used the equation for a line to find the equation for the tangent line. Um, last question here. It says, let's see, find the minimum y coordinate of any point on the curve. Justify your answer. Well, looking at the graph, we can see that that's going to be the minimum. But how do we justify that? Well, we justify that by looking at the derivative. The min is going to occur when y prime when our y prime goes from let's see, a negative value to either 0 or undefined to a positive value. So we need to find the critical points. So the critical points on this graph, um, looking at my derivative function, and you know what, I think I'm going to look at another page just so I have enough room. Um, hold on one second. All right, so we've got a fresh page here, and we want to find the minimum y coordinate of any point on the curve, justifying our answer. And so what I was saying before is remember that minimums occur when our first derivative uh, goes from negative to either 0 or undefined, and then to positive. And remember, this happens, on our derivative curve. If I have f prime of x, wherever my function goes from negative to 0 or undefined to positive, that's where my actual function, that's where f is going to have a min. So I need to think about where that is going to happen. Well, this is going to happen. The only way that y prime can equal 0 or undefined, it can never be undefined because of those squareds there, the denominator can never be 0. So it'll never be undefined because the denominator can never equal 0. When can my derivative equal 0? Well, that can equal 0 when x equals 0 or when y equals 0. Okay. Well, remember when we're looking at derivatives, let's let's think about it this way. Okay, so to find out, well, let's see, we can eliminate one of these. We can eliminate this y equals 0. Y. Well, we can eliminate that y equals 0 because if we plug y equals 0 into the equation, to the original equation, if we plugged y equals 0, we'd get 0 plus 0 plus 13 equals 0. Um, we know that can't happen. If you plug x equals 0 in, so that can't be. If you plug x equals 0 into the original equation, we get y cubed plus 0 plus 13 equals 0, or y equals negative the cube root of 13. So, our possible point here is this point um, that this is our minimum. But we need to first prove that when x equals 0, that it is in fact a minimum. In other words, um, that we're going from a negative value to being 0 or undefined, in this case 0, to then having a positive value, that my derivative is doing that. So in order to do that, we need to do a little bit of some algebra here. So if we go back to our original equation and re-express it with the 13 over there, and then factor out a y. Um, we know that the inside, because of our squares, that this is always going to be positive. And if we're always going to equal negative 13, that implies that the only way that we can always be negative, that our answer is always negative, is that this side can never be negative. This is always going to be positive. The only way that we can be negative is if this term here is negative, and that term is y. So that implies that y is always negative. So we know why the y value is always negative. Now let's start looking at our derivative equation. We know dy dx equals negative 6xy over 3y squared plus 3x squared. Um, so in order for dy dx to be greater than 0, given that our y value is always negative, in order for it to be greater than 0, x must be greater than 0, because that would make my numerator positive, because we know that y is negative, which would kind of factor out that negative, and as long as x is positive, this stays positive. And for dy dx to be less than 0, x must be less than 0, because if x is less than 0, then that's a negative number, negative number, negative number gives us a net negative. So therefore, that's a proof that at x equals 0, y is a min. And what is that minimum value? Well, that minimum value is this right here. So the minimum value is negative cubed root of 13. All right, so I'm going to stop this video, and we're going to have one more of these to watch tonight.